All right, this is question 4 from the mechanisms final exam. We're doing a review so we can get through some machine design stuff and get to the real design problems. Here is a fatigue problem, and we're going to look for the endurance strength, the fully corrected endurance strength. We're going to find the estimated fatigue strength at 1,000 cycles. We're going to sketch the SN curve for this material. We're really doing B so that we can do C. And we're going to try to estimate the number of cycles to failure if the reverse stress is 60 KSI. And then we're going to plot that point on the graph. So let's get to it. One of the things that we need to know right from the beginning is what the ultimate strength is. So we need to look up in the back of the book, normalized 4130. And if we look back there, we'll find that the ultimate strength is 97 KSI. So with this, we're first going to find an endurance strength for a sample. Right now, this is a very crude estimation, but if it's all you have, that's what you got to do. Ideally, we would have some test specimens. We'd have this number. Right? And what this prime really means is that this is an endurance strength for a laboratory sample that's very highly polished and is run under a bending conditions and so forth. And what we're going to end up doing is putting correction factors on top of this. So the way to get this number, that according to Shigley, is to take half of the ultimate strength. So that ends up being 48.5 KSI. All right. And now we're going to use that 48.5 and we're going to multiply it right here. So we're going to find SE by multiplying it by KA, KB, KC, KD, KE, and KF. All right, times the SE prime. All right, so we found that the SE prime, I probably should just put it onto this page, was 48.5 KSI. All right, this is my bad handwriting. The pen just messes up at the top of the screen. Okay, so this is the surface factor, and that ends up being an equation that's A times the ultimate strength raised to the B. Got to be careful of these A's and B's because there's another use of A and B that is not the same number, right? And you have to be careful. It's only a couple pages away. So if we look up for the conditions that we talked about that are described, I think it's a machined shaft, we find that this A is 2.7, and it's dimensionally dependent, so you have to be careful. You take 97 KSI, and it's raised to the 0.265. And again, the A and the B we look at up in a table, and we find that it's going to be 0.8033. Note that most of the time, I think probably the only time that you might have one that's different from this, almost all the time this number and the coefficients is going to be less than 1. So we're reducing. Now the temperature factor is probably, I think you could safe to say that it's going to be always less than 1, but I think there could be a scenario where it's greater than 1. The reliability, maybe if you wanted less reliability than the normal, the assumed. Now we look up the size factor. If you look in the text, if it's in bending, right, that's just 1 because the sample was in bending, so we can use bending anyway. And let's see, it's a fully shaft. Okay, so it's a shaft. Oh no, it's axial load. Excuse me. No, okay. Here's the loading factor. This is the size factor, right? The size factor ends up being equal to 1. All right, the loading factor, if you look that up, that's 0.85. Okay, that's because this is an axial loaded, and as compared to the bending, right, which the sample was done, and the temperature factor is 1. The reliability factor is 1 because nothing is said about the reliability. So, and I believe the reliability default one is about 50%, which is pretty bad. All right, so that's not the great reliability, but this type of fatigue analysis is relatively crude. So we find SE by multiplying 0.8033 times 1 times 0.85, and I wouldn't begrudge you if you didn't put these other ones in here, but I am. 48.5, and we end up with 33.12 KSI. All right, now we also need a couple other things before we can proceed. So this is actually the answer to A, right? And I needed to probably put KSI, and actually if the answer should be 33.1 in the squared off thing there, because it's 3 sig figs, and give it a unit. And so now we need to go to the next part of it, where we're looking to find this right here, SF, right, the fatigue strength at 10 to the 3. If you read this closely, you'll find that it's F times the ultimate. All right, so we look up this F right here, and that's really just based on KSI. So if we put in our 97 KSI, like there, we can find that the F is estimated to be 0.845. I believe you might be able to find an equation for this as well, or maybe I created equations just from points I took off from this and put in Excel. So if we do this and we put this 0.845 times 97, we end up finding that it's 81.97 KSI. So 82.0 KSI would be what you'd indicate as part of your answer. Now, here's where the A and the B become sort of an issue, right? Something that we need to find. Well, let me move on to the next. I think the next part of the question is to plot these points. Okay, so the first point that you plot is actually the ultimate strength over here on the one cycle. That makes sense. After one cycle, the thing would break, in the ultimate, in the test, on a test rig. All right, so there's your 97. All right, now we go to 110 to the 1000, which is 1e plus 3, and we found that the SF after 10 to the 3, 1000, was going to be pretty much 82. So that ends up being somewhere around this vicinity, okay? And we're also going to find where SF is, endurance strength is, and we found the fully corrected one was 33.12. So that's after 1,000,000 cycles. We're going to go ahead and assume that it's right there, and that's going to be somewhere like right around that location. And once again, notice that this is a log-log graph. So I'm going to use a straight edge and connect these points as best I can on a touch screen, right? And voila. All right, so we have, whoop, I didn't like that one at all. But let me see, I'll just write over it. All right, so we take a look at that and we can see that here is what was asked in, let's see, part C. Okay, now we want the number of cycles to failure. We could do this graphically if we wanted to. Okay, at 60 KSI, you take a look at 60 KSI here, and it ends up being like right around here. And wow, that's really close to 10,000 right here, right? So we could do this. We can also do it numerically, because here's where the A and the B comes in. If you use equation 614, and you will find that there's an A, totally different A than you used for the surface factor, is going to be equal to, once again, that F times the ultimate strength squared. Here I'm at the top of the screen and the thing's messing up again. And if you plug these numbers in here, you'll get 202.9. And then equation 615, you'll have a B, once again, totally different. and that's negative 1/3 the log, not the natural log, but just the regular old log, and f times the ultimate divided by SE. And we end up with, plugging the numbers in, negative 0.1312. Now that really is, these are just numbers which actually just do a curve fit on a logarithmic curve fit in this region right here. Remember that anything below here is a low cycle fatigue and is a different animal than what we want to deal with. And anything from here on out is, if it's below this level, we predict infinite life. All right. So the number of cycles based on this is going to be the totally reverse stress, completely reverse stress, divided by A raised to the 1 over B. Right. So that's going to be 60 divided by 202.9 raised to the 1 over negative 0.312. Well, no, what did I say that wrong? 1.312. Oops, could have made a mistake there. And that's going to be 11,000 cycles. So it's pretty close, right? Maybe we could, somewhere in this range right here, maybe we could have found. It's not perfect here, but once again, actually, I would say that most of the time you want your, oh, by the way, this actually turned out to be 10,780 cycles in terms of the actual number right here. But I wrote as my solution 11,000 cycles because you really only want two significant figures. This is a very crude estimation. It's one of the worst ways to find fatigue life, but it's still pretty okay. So if you had plotted a point somewhere in this region, right in there, I would say that's fine. Thank you, and we'll go on to the next problem.